Welcome back. Despite its name, logistic regression is a classification algorithm, not a regression algorithm. In this notebook, we look at a multi-class classification problem on a newsgroup corpus that's built into sklearn. I'm selecting just 4 of the categories from the built-in data set, and here we see the targets, which are represented as integers. The logistic regression function in sklearn will do multi-class classification, but we need to set up a couple parameters to clue it in on that. First of all, we set up our class as multi-class multinomial, and the LBFGS solver is good for multi-class classification. This is an iterative Newton type of optimization algorithm, and the initials here are after the names of the people who developed it. We've also specified that we want to have a balanced class weight. This notebook also shows an example of using sklearn's pipeline feature. So I've imported that here and set up a pipeline which will do the TF-IDF processing and then build the logistic regression model. In this example, having the pipeline doesn't really save us a lot of code and frankly is not that useful. But it's more useful in a situation where you might want to try out many classifiers on the same data set. Alright, and again, you can always dig into the documentation for the vectorizer or logistic regression to see if you want to experiment with any of these other parameters. Then I'm using the pipeline for predictions on the test data and printing out the confusion matrix. We see most of the observations are on this diagonal, which is good. And we see that overall we got about a 90% accuracy, which is not bad for having 4 different classes. That's a harder problem than a binary classification problem. You can also extract in sklearn, instead of just extracting predictions, you can extract the probabilities, which will range between 0 and 1. That can be useful for helping you see if the classifications were easy, like it's obviously 0 or obviously 1, or if you have a lot that are actually on the border. Now that we've seen how to run logistic regression in sklearn, let's talk about how it learns, which is quite different from how naive Bayes learned. First, we need to back up and talk about odds and log odds because this is terminology that's important to know to understand logistic regression. In casual everyday speech, we might say, what are the odds or what's the probability, and we mean roughly the same thing, but these terms are actually different mathematically. Let's say we play 10 games with a friend and we won 7 of them. Based on that information, we could say that the odds of our winning are 7 to 3, and we can express the same idea as a probability, 70%. The log odds is exactly what it sounds like. You take the odds and then you take the log of it. And so this slide is comparing log odds and probability. In a different data set, I had different values for x, and I calculated the log odds and the probability. And can't tell much from looking here, but you can see that the range is definitely not between 0 and 1 for log odds, where it is for probability. But the key difference shows up when we graph them. So when we plot them, we see that log odds is linear. And we see that probabilities are not, that they actually have this kind of subtle S shape here. We saw that the log odds range far wider than from 0 to 1. So getting classification out of that would be really tricky. What we need is some function that will scale those results to the range between 0 and 1. And the sigmoid or logistic function will do that for us. It will scale the output to be between the range of 0 and 1. And again, we see that S shape here. We can use this for classification by taking some threshold value, let's say 0.5. Anything above that will classify as the positive class. Anything below that is the 0 class. This first equation is showing us how the log odds, the log of the odds, is a linear combination of our inputs. Here we only have one predictor and its weight plus the bias, which we're now calling W0 instead of B. If we solve this for p, we get the logistic function. In naive Bayes, we calculated probabilities directly from the training data. In logistic regression, we're going to use optimization function to find the best parameters or weights, the w's in our formula. And so we'll need a loss function for that. A loss function, sometimes called an error function, tells us how much we're off. Let's say we're talking about binary classification. We can use this formula here as our loss function. The two parts are graphed here. And you can imagine that we put these two together, and it's a convex function. For optimization methods, we need a convex function. Notice also that depending on if y is 0 or 1, one of these terms is going to disappear. And what we're visualizing here is that the further we are away, either way, from the true label, the higher the penalty, the higher the loss is going to be. The chapter describes how we can take the derivative of the loss function. I won't talk about that here, since this is not really a machine learning course. But it's important to have this intuition of what we're doing. There are many different optimization methods. One of the ones that you run across a lot in machine learning is gradient descent. The idea again is that we have a convex function, and recall that when you take the derivative of something, like the loss function, what you're really getting is the slope at a given point on a line. So the way gradient descent works is it starts at a random point, and at each step it's going to adjust the weights in the direction of the gradient. So if the slope is negative, it will adjust them in the negative direction. If the slope is positive, it would adjust them in the positive direction. And that's what we see here. We see that the weights at the next time step are found by taking the weights at the current time step and updating them by the gradient. The gradient is scaled by this factor right here, which is the step size or learning rate. If we make our step size too small, then training is going to take a really long time. On the other hand, if we make it too big, we might overstep the true minimum. In machine learning, you may hear the term stochastic gradient descent. And what that means that instead of taking all of the training data, we take a random or stochastic portion of it at a time. We'll see that when we get to deep learning. In the chapter, I also talk about Newton's method, which is another iterative optimization method that's sometimes used in logistic regression and other algorithms. One of the things that we're concerned about in machine learning is overfitting versus underfitting. High bias classifiers tend to underfit. The classifier wants to see a straight line, and it will find a straight line, but that doesn't really fit the data very well. A classifier with high variance and low bias will tend to overfit the data. It's too sensitive to the variations in the data. Classifiers tend to either have high bias or high variance, and that's called the bias-variance trade-off. In the overfit diagram, the classifier tried too hard to create a really complex model that fit every training point. If a classifier does well on the training data and poorly on the test data, you've probably overfit the data. Finding a good fit for data involves first selecting the right classifier based on your knowledge about how the classifier works and the nature of the data. Other methods to find a good fit include preprocessing the data into an optimal representation, and setting any model hyperparameters that influence model fit. Here we see a model that found a reasonable fit to the data without either underfitting or overfitting. That's what we want to do. Both naive Bayes and logistic regression tend to be high bias classifiers that might underfit the data. But they're very different classifiers. Naive Bayes directly estimates the parameters from the data. That's called a generative classifier. In contrast, logistic regression directly learns to predict the target from the data, and that's called a discriminative classifier. Let's look at a couple more examples. In this notebook, we're going to look at that spam data set again that we used for naive Bayes in the earlier video. First, in this code block, I'm doing logistic regression without pipelines, and we see we got an accuracy of 98%. That is higher than we got for naive Bayes. Next, let's do the same thing with pipelines. I set up the pipeline to do two things, the vectorizing and logistic regression model, and then I fit the data, make predictions, and we get the exact same results. The next code blocks show how we can extract information from the pipeline, which can help us identify parameters we might want to tune doing something like cross-validation, which we'll talk about in later videos. From the pipeline, I'm getting all of the parameters, and you can see there's quite a few. Now that we know what those parameters are, we could dig into the documentation and make some different choices. Here I made a couple of very minor different choices, and we see that our accuracy went up very, very slightly. I have one more notebook that we can look at in the GitHub, and that's going to directly compare naive Bayes and logistic regression on a data set referenced in this paper. And here's a link to the data. It's a sarcasm detection data set that they created by combining real headlines with headlines from The Onion. So we read that in. The data set has a link to the original article, which we're not interested in. We're interested in the headline and the target, whether or not it is sarcastic. If we look at the target, here we see that it's an integer. And if we do the value counts, we see that it's pretty evenly balanced. We can also look at that in a plot. It's always great to have a balanced data set. It makes learning easier. Here I'm showing just for fun how you could make a word cloud. You would have to pip or pip3 install word cloud. And so this is the word cloud for that data set. Let's get on to the machine learning. We do our train test split. Vectorizer. Since this is a larger data set, I'm going to use this max features. So that will limit the vocabulary to the 50,000 most common words. And I only want to concern myself with words that occur in at least 2 documents. So we prepare the test and train data. First, we're going to choose multinomial naive Bayes and predict, and we get an 85% accuracy. Next, let's try logistic regression. We've set some parameters here. One of the interesting ones is the number of jobs is 4. That will enable us to train in parallel. Not particularly important on this data set since it's not that large. It's about 28,000 rows. We're using the same solver we used before. Setting verbose gives us this extra information, and you can set a random state because there is some initial randomization with optimization methods. If you ran this notebook several times, you might get slightly different results, so this is one way to kind of stabilize that. After predicting, we see that our accuracy for logistic regression is comparable to naive Bayes. They would both round to 85%, but the naive Bayes did do a little bit better. I'm going to change a couple of these parameters, maybe just one. Let's dig into that documentation. I changed parameter C, which will ease up on the regularization. What regularization does in training is it prevents the parameters that are learned from getting too large. So when we try that again, all the other settings are the same. We see that we did get a little bit more competitive with naive Bayes. But the main thing I wanted to show you was all of the parameters that you could tune in sklearn. Naive Bayes has slightly more bias inherently than logistic regression, but they're both considered high bias classifiers that will tend to underfit the data. What we want in a classifier is that we want it to generalize well. That will enable it to do well on the test data that it hasn't seen. Classifiers that overfit have more trouble generalizing to the test data than classifiers that tend to high bias.